Welcome to MAT 307 Numerical Analysis class. In this lecture, we're going to introduce echelon forms and augmented matrices. First, we start with a definition. A matrix is in row echelon form if all rows consisting of only zeros are at the bottom. So, zero rows will be at the bottom of the matrix. And secondly, the first non-zero number in the row, which is also known as the leading coefficient. Leading coefficient is always to the right of the one above it. Okay. Also, some authors require that the leading coefficient is 1, but in this course we don't. Okay. So this is optional, so we choose the option number 2, not requiring the leading coefficient to be 1. Okay, an example. The following matrices, following examples are of matrices in row echelon form. So row echelon form requires all rows consisting of only zeros are at the bottom. There is no rows with all zeros, and here there is no rows of all zeros, but here we have. Are they at the bottom? Yes, they are. And here we also have the same thing here and also here. Okay, so all the rows with all zero entries are at the bottom. So this condition is satisfied already. The first non-zero number, the leading coefficient in the row, is always to the right of the one above it. Okay, so the leading coefficient will be this one here and that one there, and as you see, it's moving to the right. So the second leading coefficient, the leading coefficient of the second row is on the right of the leading coefficient of the first row. Okay, and also here we have the leading coefficient of the first row, second row, and the third row. So it is moving to the right. So this is what we require. Okay, the first non-zero number, the leading coefficient, is always to the right of the one above it. So that means we have to have that. Okay, and here we have only one leading coefficient, so there is no more leading coefficient, so we are done. Okay, so here we have again leading coefficients are moving to the right, and also here leading coefficients are moving to the right, and also here they are moving to the right. Okay, so these are all in row echelon form. Okay, let's give an example for not being in row echelon form. So for this one, the leading coefficients of the first row and the second row are on the same position. So the leading coefficient of the second row is not on the right of the first one. So this is not in row echelon form. Here again, same happens. So the leading coefficients of the third row is not on the right of the leading coefficient of the second row. So this means we don't have row echelon form here. And also here, all zero entries, the row with all zero entries has to be at the bottom, but here it is at the top. So this is not in row echelon form. Okay, and here again one more leading coefficients issue, and it is not on the right, and here it is not on the right again, and here it is not on the right one more time. So these are not in row echelon form. Okay, some other example, sorry, definition. A matrix is in row reduced echelon form. So we have seen row echelon form thus far, but here we have also row reduced echelon form. Okay, so the definition is quite different. But the first condition say the matrix has to be in row echelon form. The condition number 2 says the leading entry in each row is 1. Okay, the leading coefficient has to be 1. And the leading entry in each row must be the only non-zero number in its column. Okay, so it has to be the only non-zero number in its column. Okay, so for all of these matrices, they are in the echelon form. So as you see, the leading entries are moving to the right, leading entries are moving to the right, and so on. Okay, so zeros are on the bottom. There is no problem at all with that. So these are all in row echelon form. Okay, what else we need to check? The second condition requires to have the leading entries being one. So leading entries has to be one, and as you see, the leading entries are always one on this matrices. So this one is one, and here we have ones everywhere, leading entries. So and here the leading entries are one, so no problem at all, and also here. Okay, so the leading entries are all ones. Okay, what else? The leading entry in each row must be the only non-zero number in its column. Okay, so the leading entry, the leading entry of this row is 1, and it is the only non-zero entry on its column. Okay, and here leading entry is here, and it is the only non-zero element, and here it is the only non-zero element, and here and there, and also here it is the only non-zero element, and also here they are the only non-zero elements, and also here they are the only non-zero elements, and here this is the only non-zero element, and that is the only non-zero element in its column. Okay, let's give an example for not being in row reduced echelon form. So for this one, the leading entry is not the only non-zero element in its column, so this is not a row reduced echelon form. So here same happens, the leading coefficient is not the only non-zero entry, and here it is not echelon neither, so because we have zero entries here and zeros has to be at the bottom. So again, this is not the only non-zero entry. The leading entry is not the only entry, only non-zero entry on its column. And here same happens. This is not the only one, only non-zero entry on its column. And here this is not already in the echelon form, because as you see, the leading entry is the leading entry on the top is on the left of the that of its successor. Okay, so these are not row reduced echelon forms. Okay, the next definition will be for augmented matrix. This is the augmented matrix for a system of equations Ax equals b is obtained by appending column B to the right of the matrix A, as this will be a matrix with two blocks. In the first block, on the left block, we will have the coefficient matrix A, and on the right block, we will have the vector of known constants. Okay, so for example, if we consider this example, this system of equations, the coefficients matrix will be on the left block, and the constant entries will be on the right block. Okay, so a matrix and a vector block. So this will be an augmented matrix. Okay, so here in this matrix, each equation corresponds to a row in augmented matrix. So this equation will correspond to that row. We basically eliminate xi's, the unknowns, but it is quite reasonable that we can basically guess we have xi's here. Okay, so we only use the coefficients. And also this equation, for example, will be the last row. So 4, 11, negative 4, 8, and 2. This is an equation represented in a row. Okay, and also each column corresponds to the coefficients of unknown. So this will be the coefficients of x1, and this will be coefficients of x2, and so on. but the last one will be only the constant. So this column will be the row, columns of the constant. Okay, a definition: two matrices are called row equivalent if one can be changed to the other by a sequence of following elementary row operations. The row operation number one is interchange two rows of a matrix. This is basically interchanging two equations in a system. So this will basically not change the solution. Okay, so this will produce a row equivalent matrix. Okay, next, multiplying a row of a matrix by a non-zero constant. Okay, so if you multiply a row by a constant, that means you're multiplying an equation by a constant, and this will not change the system at all, and it will only introduce a new row equivalent matrix. Also, adding a multiple of one row of a matrix to another. Okay, so if we add two equations, or twice the second equation to the third equation, we can still obtain row equivalent matrix. Okay, so an example will be here. So these matrices are row equivalent. So seems like we interchange the rows number 2 and 3. Okay, right, this is what's happening. In the first row, the first row is left untouched. In the last row, we also have something like subtracting the second row from the last row. Okay, so if you do that, it will be like the last row, we have 4 here. 4 minus 4, this will be 0, and 11 minus 5 will be 6. Negative 4 minus negative 3 will be negative 1, and this will be 8 minus 2. 8 minus 6 will be 2, and 2 minus 9 will be negative 7. As you see, we basically interchanged two rows and add a multiple of one row to the another row. Okay, and definition: system of linear equations said to be equivalent if they have equal solution sets. Okay, if two system of equations has the same solution set, then they are equivalent. And also a remark: equivalent linear systems are represented by row equivalent augmented matrices. Okay, that's all for today. Thanks for watching. Bye.